Good afternoon, everyone. Welcome to today's webinar sponsored by Randox Quality Control on how to monitor the effectiveness of your IQCP. Randox Quality Control is a world-leading QC manufacturer providing complete QC solutions for results you can trust. Our product range includes ACCUSERA True Third-Party Controls, ACCUSERA 24/7 Online Interlaboratory Data Management Software, and RICUS, the largest global proficiency testing scheme. Today's webinar is presented by Zoe Brooks. Zoe is a laboratory quality consultant, author, and educator who has actively practiced individualized quality control for over 20 years. And without further delay, I'd like to introduce you to Zoe Brooks.
Hello, folks, and thank you very much for joining us today. I'm hoping you can see the camera, the webcam, and the conflict of interest slide. We have to start with this, so let's get it out of the way right now. I am the copyright holder of risk-based quality grades that you're going to hear about. I invent stuff. I've also invented a bitless bridle for horses, but that's a different story. I am the majority shareholder in Awesome Numbers, Inc. They create stuff. I manage an online community and educational platform called Awesome U, where you can join me and together we can make a difference. This webinar is sponsored by Randox Laboratories. I want to thank them very much for doing that, and in particular I want to thank you sincerely for taking the time to be here today. It is co-sponsored by Awesome Numbers. They sell educational and software products for risk management. And you can also purchase courses through AACC. I believe in supporting professional associations wherever possible. What you're about to see are my opinions based on 40+ years of personal experience and research. You be the judge. They are not necessarily endorsed by anybody. I hope to prove to you today that they make sense. So welcome. Sit down, come in, get comfy. If you were to look outside my office window this morning, this is pretty much exactly what you would have seen. I work from my farm in Northern Ontario, Canada. I've done research on quality control, teaching quality control, and pretty much devoted my life to this topic. And now I live in this wonderful creative environment where I can sit here and bring my ideas to you. So please, open your mind to a new perspective on quality control. Please forgive my manners. I am going to be deliberately blunt. We're going to use some horse sense. I am going to say some things that will challenge you. I do not mean to offend anybody, but these are serious problems and we need to look at them. I want to introduce to you a process that I believe has the potential to cut lab errors in half virtually overnight. Keep your eyes on the prize. What if we could reduce lab errors by 50%. The proposal I have for you is, what if we just did a little more? And what I've learned over all these years, I have now condensed into a process that I call mathematically optimized risk evaluation. You are the first people in the world to really hear about this. When it comes to individualized quality control processes, I have literally been there and done that. I started my career, this is Canada, where I'm from, this is Ontario, this big purple dot near Lake Ontario is Toronto, and when I started my career, I took my training in Toronto, and then with 3 years experience, having turned 23 years old the month before, I became the chief medical technologist in a 50-bed hospital just outside Port Perry, or just outside Toronto, and the community was called Port Perry. So from there, it was my duty to manage quality. It was my duty to produce results that were medically reliable for the patients. That was the first year of proficiency testing. That was where we introduced computerized QC, and that was the heyday, really, of research in quality control. And that heyday continued. I moved in 1987 up to Sudbury, Ontario, so now we're 4 or 5 hours north of Toronto, and I was working with 6 small labs. These are scattered along the Trans-Canada Highway. Notice there's really not much above them. Unbeknownst to me, when I took the job, all 6 of these labs had been declared non-proficient and non-remediable by our proficiency testing program. They bought me an electric typewriter. I suggested we would do better with a computer, and within the next 2 years, maybe a year, we had installed computers in all these 6 labs, thanks to one of the QC companies. We ran DOS. We were using the internet before we knew what the internet was. I would go up to these labs, pick up a 5 1/4 inch drive it back to Sudbury and say, well, if I can carry that data, we must be able to transmit it. So these were really the early days of quality control, but what we did back then, and you'll recognize this, some of you as a dot matrix printer, is we actually set allowable error limits. Sorry, I'll go back to that. I hit the button too soon. We set allowable error limits for every single control. Every month we measured bias, we measured total error, we calculated critical systematic error, and we individualized the QC rules that we needed for every single QC sample in 5 departments across 6 labs. What I want to do today in 45 short minutes is cover a very long agenda. The first question, so we want to come up with a process that will let you do exactly that, to manage risk. The first question you have to answer is, how good is good enough? How do you set medical goals and acceptable risk levels? That's a new term. Is your method good enough now? You have to evaluate current risk. Current risk is driven by the analytical process. Has nothing to do with the QC process. Is the method turning out good results now? The next thing we'll talk about is how to design QC processes to detect unacceptable current risk. There is a line that you can draw between acceptable risk and unacceptable risk. Your QC processes must detect unacceptable risk. This is new. You have to set the QC frequency to ensure acceptable potential risk levels. This is really what the patients want to know. What is my risk of a bad result today? And if we have time, we're going to get to this final little trick where you can simply ask the question, is this a risk-based quality grade A test? And in that one question, you can evaluate patient risk and QC effectiveness. So hold on, send in your questions. We have a team of people here looking to field questions, and I'll get to as many as I can at the end of it. And we're going to cover this big agenda as quickly as possible and as thoroughly as possible. The most important test that you will ever do in quality control is what I call the DIMS test. Does it make sense? I've taught for over 10 years an online university course in clinical lab data analysis. And there were a few tricks I introduced, and one of them was the DIMS test. You can just say to people, that fails the DIMS test. So let's try that out. Does it make sense? Lab errors exist. Yes, they do. Lab errors harm patients and waste money. The current rate of lab errors is acceptable. How sure are you about that statement? Labs are talking about doing less QC. Does that make sense? These are the questions we're going to answer. You're not going to see a fishbone diagram. You're going to see very few quotations of regulations. You're going to see things that make sense. Before we get into the how of monitoring the effectiveness of your IQCP, it is really, really important to understand what it is and why you should do that. There are very good reasons beyond just the regulations. There are 2 documents people are talking about. One is IQCP, a step-by-step guide developed by CMS in the United States, and the other is EP23A, a laboratory quality control based on risk management. This is a regulation for people in the United States. In light of advances in technology, CMS has adopted a risk-based approach that they call Individualized Quality Control Plan. portions of EP23A of the EP23A document capture the principles of what they want to do. This EP23A provides guidance on how to meet these regulations. It also provides guidance on how to manage risk in general in labs. You must do IQCP, you should do risk management. There are two new things that these introduce. One is, at the least, the ability of the QC procedures to detect medically allowable error should be evaluated. For the first time, you have to QC the QC process. They say the same thing in IQCP. Remember, quality assurance is used to determine if the quality activities you have put in place are working. Are they doing their job? And part and parcel of making that decision is the frequency of QC sample procedures must be designed to have a high probability to detect a stated medically allowable error. Very clear guidelines. Risk management is actually black and white. You have, it is or it isn't. It's a remarkably clear process. Risk evaluation is the process of comparing the estimated risk against given risk criteria to determine its acceptability. So you set an acceptable risk level, you measure the existing risk, and you answer the question, is risk acceptable, yes or no? Here's the trick though. It's not your call. That question, is risk acceptable, yes or no, belongs to these people now. Acceptable risk is defined as a state achieved in a measuring system where all known potential events have a degree of likelihood for a level of severity of an adverse outcome small enough such that, when balanced against all known benefits, perceived or real, patients, physicians, institutions, and society are willing to risk the consequences. I must admit, the first time I read it, my thought was, and why don't they throw in world peace? This is obscure, this is impossible. It is perhaps a tad obscure, but it is not impossible. The best analogy I came up with is they test fire alarms, don't they? There is a risk of catastrophic harm from fire. Because we know that risk exists, we identify fire hazards, we conduct inspections, we do everything we can to prevent them, we train people. We don't stop there. We install a fire alarm system. So if all this preventive measure doesn't work, we still install an alarm to catch a fire if it does break out. And we don't stop there. We test the fire alarm and we hold fire drills. Take that into the clinical lab. There is a risk of catastrophic harm from medically unreliable results. You identify the hazards that can cause unacceptable patient risk. You carry out inspections, you do method validation, you do routine maintenance, you do proficiency testing, you send your key operators out for training, you do everything in the world you can to prevent that risk. But in case there is a problem, you use instrument built-in quality control, patient QC, and stable sample QC are the tools that you have to make sure that risk does not exist, and now you can't stop there. At the least, the ability of QC procedures to detect medically allowable error should be evaluated. When you've done that, then you have acceptable risk. I'm sure a lot of you have seen presentations already on EP23A. They list all of these failure modes that can happen. All of these things can go wrong with your analytical process. I have seen every single one of these. I have seen every single one of these detected by statistical QC. The question you have to ask is, can you detect all of these and more without stable samples and statistical quality control? Yes or no? If your answer is no, then go get a cup of coffee and enjoy the next part of the hour because it's not going to pertain to you. But if you think that you cannot identify all of these errors immediately without stable sample QC, then stick with me and I'll show you how to do it. It's not impossible. Acceptable risk in QC is a state achieved in a measuring system where errors detected by statistical QC, those are the ones we've narrowed it down to, have a current risk level for medically unreliable results causing significant patient harm, clinical or legal costs, small enough such that when balanced again the avoidable patient harm and clinical costs that you could achieve if you practiced more QC and lowered the risk level, patients, physicians, institutions, and society are willing to risk the consequences. Why would you do this? Why would you do this if you didn't have to? Do it because I believe, and I hope to convince you today, that mathematically optimized risk evaluation, this is the process we're going to talk about, can cut lab errors, the existing lab error rates, in half. That would mean eliminating about 2.5 million errors in the US. There's a study done relatively recently where they said calcium error alone can cost $200 million. If we can cut error rates in half, perhaps we can do that with just a little more than the existing statistical QC. There are two components to risk management. There's the current risk that's created by the analytical process, and there's potential risk that's driven by the QC process. This answers the question, is my risk of receiving a medically unreliable result today acceptable? And this says, will my risk still be acceptable if the method fails tomorrow? Now you might have patients, physicians, etc., or their advocates coming into your lab and asking those simple questions. The analytical process creates numbers. The QC process verifies the numbers. You only report bad results if both these fail. So if the results are good and the QC says they are good, there's really no harm to the patient. If the results are good and the QC says they're bad, there's minimal risk to the patient. You might delay their results. If the results are bad and the QC says there's bad, well, you've caught the result, the error, hopefully in time, and there's minimal risk to the patients. What we're concerned about is when the results are bad and the QC says they're good. We ask that question in a very practical setting. I have a study that I'm going to share with you now. There are 605 QC samples. We're going to see three groups in total. I've combined in this instance the two groups that did not use any process, any computer program or anything to mathematically optimize their QC. So this is an assortment of, I think, maybe 20 labs between the year 2000 and 2014, and we asked how many of those 605 QC samples would identify a simulated clinically significant error in the first run. So I simulated a shift that caused 2%, not 5% of the results to fail, and 34%, only 34% caught it in the first run. If we mathematically optimize the QC process for those exact same analytical processes, we can bump that up to 72%. So mathematical optimization, letting the computer balance all the variables that are involved in quality control. If you plug those numbers into a computer, instead of having hundreds and thousands of individuals try to do it themselves, you come up with a significantly different and more consistent process. How are you going to do this? Great, I want to do it, but how? This is where you are now. We use recommended TEA limits based on state-of-the-art or statistical limits that are defined by lab scientists. Local allowable error limits, if defined, are set by the medical director based on personal opinion. The QC processes that I have seen are inconsistent, unverified, and ineffective to alert staff to clinical failure. I apologize, that is what I've seen over and over again. Staff understanding of and response to signals from QC charts and rule is inconsistent and unverified, and if methods fail, more than 50% of patients will be exposed to the risk of medically unreliable results. That's where I see us today. I keep saying, somebody, please stand up and prove me wrong, please. If you want to change that, here's what we can do. We can use recommended medical goals and acceptable risk levels designed for general clinical settings by medical practitioners, the people who are going to use them. The local medical goals and acceptable risk levels are managed by the medical director and approved by local medical practitioners. Automated QC design verified to alert staff immediately to unacceptable risk levels. We can replace what everybody's doing today, QSign, that is pre-verified. We can create verified education and competency assurance to confirm that staff can take the right action to mitigate risks. And if we want to change this, if the method fails, now less than the defined acceptable number of patients will be exposed to the risk of medically unreliable results. That's the change that I'm recommending. We have a lot to digest in a few moments left. We're going to start first about setting medical goals. And pardon me while I take a breath and check the time. 2:52. We're doing okay. Risk management is black and white. Lab results answer 3 questions. Might you have it? Do you have it? Is it getting better, worse, or is it stable? Patient risk is acceptable in your lab when the odds are good enough that your clinicians can reliably answer these questions for your patients. It is all on the shoulders of the medical director. As the lab director, you are responsible. It is your responsibility to ensure accurate and reliable patient results. In order to do that, you have to define what is accurate and what is reliable. And you have to ask the question, do medical needs of patients change when the clinical chemist crosses the street? Right now, we are using as many as 10 ways to select medical goals. And yes, and I used to teach this. Here are your 10 steps to select medical goals. But there may be 10 ways to do something, but there is only one best practice. There is only one truth. The medical director can set quality goals for this method in this setting so these doctors can treat these patients reliably. That's nothing new. They've been saying that for 40 years. They said it in 1976. Analytical goals can only be defined in terms of patient care. Any other basis is irrelevant. But we didn't do it. So they said it again in 1986. And they also talked about selecting rules appropriately. But we didn't do that either. Now in 2014, we're saying this again. We've had another meeting in 2014, the Milan Consensus, that again says your #1 choice of allowable error limits is based on the effect of analytical performance on clinical outcomes. Medical goals. So what are you going to do differently this time is my question. If you always do what you've always done, you'll always get what you've always got. If we approach changing to risk management the same way we've approached every other new QC document that's come out, it's going to make the same amount of difference. Why not just ask your medical staff? What if all your staff walked around with a t-shirt that said, I'm a medical doctor and I approve these medical goals? That's what we did. We sat down with our medical director. These goals were set by Dr. George Mazzarella, medical director. They predate the CLIA limits. You'll see they're slightly different. This is not 10% that we're using. We just sat down with the medical director and said, what's good enough? He was able to answer that quite comfortably for 95% of the tests, and for a few, he went off and spoke with the specialists. We calculated bias, total error, critical systematic error every single month, and we individualized the QC rule for each QC sample for each method every single month. What happened in those labs, remember they were all declared non-proficient and non-remediable. Within 2 years of instituting this, we went from getting 7 to 9 letters of concern a month to 0. For 6 labs of serious concern in a year, we had 0 letters of serious concern. That is how dramatic a difference it can make if you manage your quality to meet patient needs. Your proficiency will come in line.
Hi, Zoe.
Yes.
Hi, Zoe. This is Kim. I'm one of the organizers. Could I ask you a question here?
Yes, please do.
I come from a hematology background. For the other attendees, I also care deeply about quality and have seen some of this work previous to this, and I think she really does have something that needs to get out here. And my question is, though, does this new process of using risk as a quality goal work in other areas of the lab, not just chemistry?
That's a great question, Kim, and thank you for bringing that forward now. Yes, it does. We did it for chemistry, hematology, coag, blood gases, and what we called special chem. We actually have a group now looking at this for molecular testing and infectious diseases. It's a remarkable process. It says, what's good enough? What have you got now? This is a quality management process that goes anywhere and lets you answer the question, is my quality good enough? You can see that we quantified risk. So you've got to answer the question, how much risk is acceptable? Well, how much risk exists today? So we looked at 3 groups of labs. I call them the good, the bad, and the ugly. We had 378 QC samples from the year 2000. They had old methods, but they used QC software. We compared them initially to this group that had the same old methods, and they used people to set up their QC strategy. And now we have 233 from 2012 to 2014, and these people have new methods and people that have 10 more years of training. What are we going to see? We quantified the risk. What percent can produce less than 1 bad result in a million, and what percent of methods have over 1% risk. You can measure risk directly. If you want to do this in sigma speak, it means your sigma is 5.2, or here your sigma is less than 2.33. Every sigma can be converted to a risk level. So these are the good. 73%, back in the year 2000, 73% of their methods were producing less than 1 bad result a million, and only 3% had more than 1% of only 3% of their methods produced more than 1% errors. The percents get confusing. 3% of the methods with a 1% error rate. How did that compare to the people with the old equipment? Well, not surprisingly, there wasn't a big difference. There was a 5% difference in the number with error rates less than 1 in a million, and as expected, when they used individuals in all these different labs instead of a consistent QC process, now double the percent produced results, double the percentage of methods had more than 1% error rates. So what did we accomplish in 12 to 14 years? What will it be? Will the risk be better? Will it be less? Now we had 70% with only 1 bad result in a million and 5% error rates. I really expected, with the improvement in the analytical processes, this would have been dramatically different. And it wasn't. It's the reality of this, being able to see these numbers, that has me so convinced that I must be speaking with you. When you look at this in bulk, there's nothing here that you don't know. There's nothing new in the science. What there's new in is the evidence and the bulk of the evidence. So come back to that question. How many results can fail your medical goals? How many doctors are going to walk around with this t-shirt? I'm a medical doctor, and I demand these medical goals for 95% of my patients. How many results can fail medical goals before you stop reporting and fix the method? What are you going to do if patients, physicians, institutions, and society walk in and say, hey, I want 100% chance that I'm going to get a good result? Can you do that? Those are great questions. How much risk is acceptable to the people who matter? Well, let's look at something that many people can identify with, because you probably all know somebody who's getting blood thinners and monitoring their ProTime or INR. You're going to say medical goals are set at, now the two most popular choices are regulated limits of 15% or biological limits of 5.7%. That's a big difference. Our stable risk level, so the probability of results failing that medical goal, is less than 5%, 1%, 0.1%. Our QC processes ensure that no more than 20, 50, 100 patients will be reported if risk rises above that level. These are the numbers you need to fill in. When a doctor works both at the hospital on the north side of the street and the south side of the street, I think you're going to have trouble convincing him that on one side of the street, your INRs can be 3 times as lax as on the other side, or vice versa. What is the stable, do you want to turn out 5% medically unreliable INR results? How many patients are you willing to expose to unacceptable risk? Is this good enough? This is from Mosby's Medical Dictionary. This is another thing that got me riled up. Allowable error is the amount of error that can be tolerated without invalidating the medical usefulness of the analytical result, without making the result medically useless. Allowable error has a 95% limit of analytical error. Only one sample in 20 can have an error greater than this. 1 in 20. If you look up the definition of allowable analytical error, it's a systematic error that is acceptable both statistically and analytically. I don't know what that word analytically means there, and if you do, please write to me afterwards. So, Ray, can you please launch the poll? It's time to get you involved. Does it make sense that one medically unreliable result in 20 is acceptable? Now we'll see how the technology works. Ray, over to you. And I see that the poll is open. There are 3 or 4 steps. You have to open the poll, close the poll, open the poll, share the poll, close the poll. There's another step that I'm missing in there. Poll must be open to enable screen sharing. Is the poll open? Is everybody seeing the poll? Can some of the other panelists come in on that one? Or Ray, can you speak, please?
Sure. We do have 72% of people have voted. So everyone must be seeing the screen.
Just let me know when it's...
Yeah.
Excellent. Perfect. When it's near enough to complete, would you please read the results out for me?
Sure. So far, with 78% of people voted, we're at 60% no never and 36% sometimes.
Okay. Well, let's close the poll then. I think that speaks enough. And we are on a time frame. It is 3:04 and we're supposed to finish this in 15 minutes, and we're certainly not going to finish it all. It's more important to understand some of this thoroughly than to get through all of it, and that's exactly why we scheduled a Q&A session 2 weeks from now. Okay, I hope everybody saw the results of the poll. So, how can you set medical goals and acceptable risk levels? Well, theoretically, it's really not that complicated. You select these analytes, in these clinical settings, and in this setting, I'm going to use the published standard, our medical policy, this or the policy set within the lab, and my acceptable current risk level is this. Once you set these numbers, the rest is pure math. You plug in your measured mean in SD, and everything from there on is automatic. It's curious that so many people do not think that 5% is acceptable, and yet the recommended processes for designing QCs, the recommended way to design QC processes generally allows for a 5% error rate. Anytime you're using 1.65 in your formula, you are allowing a 5% error rate. So is it good enough now? I measure margin for error, and I apologize to all the Six Sigma people. I measure margin for error because it can be taught in a matter of 5 minutes. Everybody knows what margin for error is. You don't need to mention statistics to teach margin for error, and there's only one way to calculate it. You can't get it wrong. Which one of these cars, if this is a car going through a tunnel, the tunnel represents your medical goals. If you move half your distance to the right, which one's going to crash first, the wide one or the smaller one? And this time it's the wider one. This would represent a method with wider imprecision. When you set up your risk levels, you're really saying, how much of that car am I willing to sacrifice? Do I want to make sure it doesn't even scratch the paint on the mirror? Can we knock off the mirror because we've got to get through this tunnel and it's important, and still get through? Am I willing to scratch the paint on the car? What amount of risk are you willing to endure before you stop, before you crash, and fix the method before you get there? You can convert margin for error directly to a % risk. A margin for error, you can set it so that it hits 0. The beautiful thing of a margin for error is 0 is always unacceptable. You set it up so that margin for error becomes 0 when your desired risk level is unacceptable. I set this one up for an acceptable risk level of 2.3%. That means my margin for error there is 0. If I have a margin for error of 1, it's virtually 0%. If my margin for error is minus 0.35, that's equivalent to a sigma of 1.65, and that's a 5% error rate. If my margin for error is minus 1, that's a 16% error rate, and that's a 1 sigma method. Another reason I prefer margin for error above sigma is it is so intuitive that when the method is 0, things are bad. When we come back in 2 weeks, we are going to go into this simulator and spend a significant amount of time in it. And you're going to see there that every time you change any one of these 5 numbers, your peer mean, because that is the best source of the true value, your current mean, your current SD, the medical goal, and the acceptable risk level, those 5 numbers, whenever they change, your current risk acceptability changes. And we have this simulator set up, but we just don't have time to go there today. So we're going to get a little bit further into potential risk. You're going to have to come back to see it in action. You can plug these numbers into the simulator, and it will tell you for thousands of controls, is risk acceptable, yes or no. These 5 numbers drive the acceptability of the current risk level, and these 2 numbers, the results per month and the total risk, and the cost of each medically unreliable result, that's the average clinical or legal cost per medically unreliable result, those drive the total risk and the total cost. You don't control these numbers. You can't go in the lab and just tweak something and make that happen. You might be able to go and get a new reagent lot. You might be able to go and recalibrate. But changing these numbers are really not within your control necessarily. You might have to call for maintenance. You can manage those numbers. You can use those numbers to calculate if risk is acceptable with numbers that you can just calculate, or with math you can use to calculate the numbers in your head. So in this example, you have a true value of 100, an allowable error limit of 12, a measured mean of 100, a measured SD of 2, the absolute bias is 0, 100 minus 100. The total error is the bias plus 2 times the SD. Anybody can multiply times 2. Once you have your total error, you subtract it from the allowable error. The allowable error minus the total error gives you your margin for error, and your margin for error divided by the SD gives you the number of standard deviations. You can do this with your staff. You can do it as an exercise because this takes no statistics. It's simple: add, subtract, multiply, and divide. And when you know your margin for error, then you know if risk is acceptable, and you can then use that to design your QC process. How are you going to design that QC process? Next tough question. Which of these products can be released to the customer before verifying it meets customer specifications and regulated standards? The glucose tolerance drink you gave to the patient, the reagent you used, the standards you used to calibrate, the linearity or trueness samples you used at method validation, your QC samples, the proficiency result, the patient result. When was it established that it is okay to report lab results before checking the QC? They manufacture all of these on a continuous basis, but they don't ship them to the patient until they've checked the QC. And that is a reasonable question that patients and society might come in and ask. These guys might want a 0% risk. We used to bracket QC runs. We used to test the controls and say the control is okay. We would run the patients in the QC. After we checked the QC at the end, then we would report the patients. We bracketed the run. We would bracket the next run. We would report the patients. In the next run, if the QC was unacceptable, we would not report the patients. 0 risk, as long as you're sure you can detect that error immediately. The principle of testing QC samples is that measuring system failures that would negatively influence the testing of patient samples also affect the results obtained with the QC samples for many, but importantly not all, failure modes. If you are testing QC samples, the assumption is they mirror the patients. If you don't know that they mirror the patients, A, why are you testing them? And B, how do you know your patients are okay? The fact that your controls must mirror the patient is one of the givens in establishing your QC process. What we do now, the analytical process creates the patient and QC results, we report them, we check the QC. We create results, report results, check the QC. Now we get a QC reject, but what if the method actually failed way back here? At the least, the ability of QC procedures to detect medically allowable error should be evaluated. How you do QC drives potential risk. This is the survey that a few of you took, and it reflected very much this. Everybody picks and chooses their mean, SD, and QC rules in a different way. There are not 192 right ways to do quality control. There is one recommended way to do QC. But everybody does it differently because you've never been asked to prove before that it works. The optimum QC process is a calculation. It's not an opinion. We ask people for this, some of you went and took the survey now, and the measured mean from a single recent time period is what is recommended for your QC chart. That's the number in black. When you get to the assigned SD, either of these will do, but still less than half of the people are doing what's recommended. And it's the same thing. For years now, you should modify the QC rules to match each test depending on its performance, and less than half the people do that. Wrong is wrong, even if everybody is doing it, and right is right, even if you're the only one. A lot of these messages, including that one, came to me from the horse world, where people realized that after centuries of thinking they had to stick an iron bit in a horse's mouth, they truly don't. So you can do things differently. Many, many people care about quality control, but they don't all care about statistics, nor do they have time to get into them. This problem that I'm talking about, please, it is not your fault. It is your problem. This has happened over the years. It happens everywhere. I've traveled pretty much around the world. I've been in hundreds of labs. I have never been into a lab where they actually did all their QC according to how it should be done, except perhaps with those ones that used the software. For the frontline staff, advisors, and managers, this is your opportunity. Risk management can make your life black and white for QC. And these guys can help. We are at 3:16. I'm going to find one slide. Oh no, I'm going to want to show you this one first. Let me show you the impact of mathematically optimized risk evaluation. So these are the 605 labs. This is what they're doing now. We measured how many methods can detect clinically significant error in one run. 33%. And would, if you mathematically optimize the QC for those same processes, you eliminate all of these that never see a QC flag, and you bump up the number that can detect error in the first run from 33% to 72%. If you more than double the number of errors you can detect, surely that will cut down on the errors reported. This is what we saw, and this I've never seen before, and I'm taking a few extra minutes to share with you today. Potential risk, the probability that people will be exposed to unacceptable risk if the method fails, is driven by both QC design and QC frequency. The patients at risk equals the patients per run, and the patients per run is determined by your QC frequency, and times the R to R, which is the runs to reject. So it's a simple equation. Patients at risk equals patients per run times runs to reject. If we looked at, as the margin for error decreases and the analytical process quality got better, you can see a direct relationship between the mathematically optimized QC processes and the potential risk. This is the number of runs to reject. None of them were above 10. This is what we saw with the lab QC. All of these are up above 10. In fact, they would never detect a clinically significant change, and there is no relationship whatsoever. So now that I've significantly rained on everybody's parade, I'm going to finish very quickly with the flow chart that will make this easy for you, and then we're going to open it up to questions and answers and hope that you will indeed be back in 2 weeks. So let me show you how this works once you've set it up. You define your medical goals. Results are medically reliable if they are within X% or Y units of the true value. You define acceptable risk levels, current risk and potential. What % of results can fail before you stop reporting errors and correct any that have already been reported? What % of results will be exposed to unacceptable risk after failure? Estimate your current risk Evaluate risk. Is it acceptable? If it's not, stop. Go fix it. If it is, then estimate the potential risk. What % of results will be exposed to unacceptable risk after a simulated clinical failure? Evaluate your potential risk. Is it within your defined limits? If it is, so if your current risk is acceptable, potential risk is acceptable, that is grade A, good to go. If it's not, you can implement the recommended mathematically optimized QC process and come back down the list. Did that fix it? If that QC process didn't fix it, then you can also recommend the mathematically optimized improvements in accuracy and precision. And if that fails, you have 3 landing spots. Down here, you don't need to stop, but you do need to modify your QC frequency to maintain acceptable risk. You need to increase the chart review and improve or replace the method. I'm going to go through very quickly where you can go to from here and then open it to questions. If I am right, and I can convince you that I might be right, this can help millions of people and save billions of dollars.
Unmuted.
Perhaps it can improve quality in general. This is a different process to manage quality. Now it's up to you to see where it goes from here.
Muted.
You can come back for the Q&A webinar on July 8th. You're already registered. We'll use the QC simulators. We'll talk about Six Sigma
Unmuted.
studies. We'll go through your questions and give you an opportunity to roll up your sleeves and do something. In the meantime, you can go to Awesome U, where you can collaborate with other people and find more information. There's a place here for webinar Q&A and discussions, so you can come here to discussions, connect with other people, and submit questions for the next webinar. At AACC and ASCLS in Atlanta, please do visit Randox. We are very grateful to them for sponsoring this webinar. I'm presenting a brown bag session called IQCP DIY, Individualized Quality Control Processes, Do It Yourself, and Kim and I are presenting a poster, Risk-Based Quality Grades, an Alternative to Sigma Metrics. If you want a better quality management system, ask for it. I've been using this slide for 10 years now. They won't build it. You don't have this. This has existed for 20 years. You don't have it because they won't build it because you haven't asked for it. You haven't asked for it because you don't know it exists. You don't know it exists because
Muted.
you build it. And I've been going around and around and around this circle for 15 years. Now you know it exists. You will be receiving an email to say, here's where you can go and say, this might be a good idea worth checking out. All right, I'll pick this last slide up and open it up to questions. And
Unmuted.
Do we have questions, Ray?
Yes, actually we've got a few questions. The first one is, can your method, or is your method applicable to esoteric tests like cytogenic testing, or only to POC?
That is a wonderful question, and it's almost the same question that the people with molecular are talking about. There's something I'm concerned about in there if the things are logarithmic. I have used this in cytogenetics many years ago, and it certainly did seem to work. We applied it. So you'd have to model it. But it should, as long as your QC sample represents your patients, this process will work.
Yes, and in the follow-up question, it was just in those cases, how is it feasible for highly manual, and I'm not sure exactly what this question was, but for highly manual and often difficult to even get all in writing. So I'm not sure exactly what that meant, but
there are some tests that are just very, very tricky, and they're difficult to do, they're challenging, it's hard to get them right, it's hard to know if they're right, and there's a very small peer group. A couple of things you can do. For one thing, you're not all alone. So connect with the other people. Connect with other people at AwesomeU. That's what we're doing here with the molecular biology and so with the molecular testing and so on. So here you can come and join. Even if you're not in a peer group, you can connect with other people with the same problems. And then we can model the data, because I love simulating data. I love real data. So we can model it, we can see what works, if this works, what doesn't work, how do we tweak it. It's going to take a bunch of people working together to see what works. For me, the difference, and in the teaching, the difference has been those simulators, that when people can actually see, when I change this number, this is what happens. So this is why I created this, so that there will be a place for people to get together and work on projects like this. Hope it helps.
And I think that was it for the questions, Zoe.
Okay. Wonderful. We are pretty much on time. I would maybe, if we've got 1 minute.
Sorry, Zoe. Zoe,
yes?
Can I just interrupt? There was a few just really last-minute questions, or last-second questions. How about for microbiology labs?
If you're non-numerical, no. You need numbers. At the very least, you need numbers. And I don't think MIC type numbers work either. You need numbers that behave in a very predictable fashion and controls that represent that. So this is all based on Gaussian distribution. If the numbers you're dealing with are non-Gaussian, we need to be aware of that, and that's not something that only applies in infectious disease testing. There are a lot of tests in the chemistry department where the patient population is logarithmic. There are a lot of questions that we should be asking. There are a lot of things that this process highlights, and I know this is a lot of information in a very short time, but you can see differences between analytes as well as between QC processes. I have seen so much new information since we started doing this, and it's not that I didn't know it was happening, but when you can see it in action, so you can see that a lot of these are not getting as many grade A methods as they can, but there's differences between the analytes, even with, you know, or mathematically optimized QC. Sorry, there are a lot of methods that you just cannot eliminate all of these grade Ds. So you see these protons, INRs, sodiums, these are difficult methods. These are grade D methods, and in a grade D method, it is impossible to detect the change in the first run with a 1-2S rule. About 30% of the methods we've tested in every lab fall into that category. If your margin for error is less than 2, and that means if your sigma is less than 4, you're trying to detect a shift of 2 standard deviations. Well, you know from your basic math and Gaussian distribution, if the mean shifts 2 SD, 50% are above and 50% are below. You've only got a 50-50 chance of detecting a 2 SD shift. 30% of the methods fall into that category, and we're not identifying them with the QC we're doing now. It's a totally different way. We're using the same logic. It's all built on the Gaussian distribution. There's nothing new. We're just looking at it from a different perspective. And it's going to take more looking, and I hope you will get involved to do this.
Okay, we had another question. How does a lab using automatic QC factor in for IQCP? We are using GEM 4000 using IQM process.
Not familiar enough to really try to answer that. In an ideal world, this process would be tied right into your QC system. So in an ideal world, in the future, what you will see is throw your QC data through what we've created here, and pardon the commercialism, is essentially a software app that can be added to any QC software. It should be added by your QC software provider. You throw your current data, you've got the numbers, throw it through that app, and it answers the questions: is current risk acceptable? Will existing QC detect failure immediately? Do you have minimum false positives? If you don't, it's a grade A method. If you've got false positives, the computer will tell you how to optimize that system, or in the future, this will all be automated. When the computers, when it says, hey, use this QC process, why not let the computer do it? We've let computers take over everything else. They're parking our cars for us, they're driving, they're flying to Mars, and we haven't turned over. There are at least 12 variables you're trying to balance when you're trying to design the QC process. I think it's been proven. I've decided I cannot teach it. I cannot teach it in the time provided well enough that people can be proficient. But I can make people proficient within the 10 hours they have at school if they would let the computer tell them if the risk is acceptable or not. We're going to, at some point in time, have to make a decision. Are we going to keep doing what we've always done, or are we going to do something different? And one of the webinars I listened to was, and I apologize, I forget his name, a doctor out of England, who said, is it going to be the lab that leads this charge, or will it actually be physicians' society when patients hear that they can perhaps get a grade A lab test? They might want one. I think we should shut it off. We're at the end of our allotted time. Sean, did you want to?
Yes, just like to thank everyone for attending. We at Randox Quality Control, we're really looking forward to bringing more QC webinars in the future. If anyone does have any questions about today's webinar, they can email us at qcira@randox.com, and don't forget you can also visit us online at randoxqc.com or at AACC stand 1335 as well.